Carbon dioxide, CO2, is foremost among anthropogenic greenhouse gases in concentration and effect. It constitutes about one-third of the global warming that derives from human activities. Concentrations of CO2 in the atmosphere depends on the global carbon cycle that accounts for the fluxes of carbon among various storage pools. The vast majority of carbon on Earth is part of limestone, calcium carbonate, and other sedimentary rocks. Weathering of rocks, as well as the high temperatures used during cement processing, releases CO2 from limestone, and the CO2 enters the atmosphere or dissolves in bodies of water. Photosynthetic organisms absorb CO2 from the atmosphere or bodies of water and then use solar radiation to convert this low-energy carbon into the high-energy carbon in organic compounds. This process reverses when organisms respire or when they die and decompose. The CO2, which is thus released, once more enters the atmosphere and dissolves in bodies of water. Fossil fuels derive from organic carbon compounds formed during decomposition of prehistoric organisms. Burning fossil fuels rapidly oxidizes these compounds and releases CO2. Carbon exchanges among the atmosphere, soils, and vegetation and changes in land use are balanced as are exchanges among the atmosphere, ocean, surface, marine biota, and dissolved organic carbon. Out of balance are carbon extractions from sedimentary rock and from coal, oil, and gas deposits, and carbon emissions from fossil fuel burning and cement processing. Global carbon dioxide emissions from the burning of fossil fuels grew nearly 60% from 1980 to 2006. All areas of the world participated in this growth with the exception of Eurasia, where emissions declined in 1991 after the breakup of the Soviet Union, but are now rising again. China surpassed the United States in total carbon emissions during 2006, although the United States still leads in emissions per person. Carbon emissions from China tripled between 1980 and 2006, and its contributions to the world's total emissions jumped from 8 to 21%. Emissions from the United States increased 23% over the same period, yet its contributions to the world's total dropped from 26 to 20%. Various scenarios about future demographic, social, economic, technological, environmental conditions result in a range of predicted global carbon emissions. Scenarios that assume rapid economic growth and reliance on fossil fuels, such as the A1FI scenario, or regional autonomy, the A2 scenario, will nearly triple the rate of carbon emissions during the 21st century. In contrast, scenarios that assume the adoption of alternative energy sources, A1T or B1, will generate a rise in emissions until the middle of the century and then decline. For the intermediate scenarios, A1B or B2, carbon emissions will about double and then level off. Additional carbon released by human activity suffers several fates. Most of this carbon remains as carbon dioxide in the atmosphere, and atmospheric carbon dioxide concentrations may increase between 50 and 300% during the 21st century. About 1/4 of this carbon has dissolved in the oceans from 1800 to 1994, and more is likely to do so. Vegetation has assimilated some of this carbon through photosynthesis, and organic carbon compounds have accumulated on land and on ocean floors. Global warming, however, will accelerate respiration and thereby will release more carbon dioxide from this organic carbon. Some global climate models, such as the one from the Hadley Center, predict that by the latter half of the 21st century, respiration will exceed photosynthesis, and so land masses will become sources rather than sinks for carbon.